Thanks very much for the introduction, and it's really a pleasure to be here today at this set of final workshops with 2021 to present this session on adapting to climate change bit by bit with planetary health, informatics, and machine learning. Thank you very much for joining. And just a quick note to say that I'll try and answer questions in 5 minutes, dedicated 5 minutes towards the end. So if you'd like to enter your thoughts into the chat as they come, we'll try and take them then. So really briefly, my own background is in biomedical engineering and health informatics. And for this talk today, I can really take very little credit or none at all for the work that is going to be covered in this. I'm just the lucky person who has the privilege to present this, what is the work of many colleagues in the field of data science and artificial intelligence from really all over the world. So in the next 40 minutes or so, we'll go through an overview of the planetary health problem. And my job is going to be try and convince you of the role of data science as part of the solution. So we'll begin by taking a sort of a bird's eye view of the issue of climate change, how it's linked to the issue of planetary health. And then we'll look at some of the examples of data science applications and solutions in healthcare. Finally, we'll look at some of the challenges in planetary health analytics and highlight some areas where hopefully you'll be convinced by then that we as data scientists can contribute in different ways. So one thing I should mention at this point is that what we won't cover in this talk is theory. So there'll be no climate science or machine learning theory as such. In fact, if I've done this right, and you may be pleased or disappointed, depending on your aptitude to know this, that there will be really no maths. Okay, so to look at the issue of planetary health, which is defined as the impact of human-induced planetary changes on the health of human beings itself. We could start by looking at these images of our rapidly warming world. And these were behind the science that led to the famous Paris Agreement in 2015, where for the first time world leaders set the goal of limiting global warming to within 2 degrees. And by looking at this closely, we can kind of see why. So on the left side is what's known as the net zero scenario, where if we achieve net zero carbon emissions by 2050, we can hope to limit the global warming by the end of the century to under 2 degrees Celsius, where 2 degrees is the critical tolerance threshold for human health, according to the International Intergovernmental Panel on Climate Change. So that's the importance of the 2 degrees. And on the right side is the business as usual scenario, if you will, where at our current rate of emissions, the world is set to be 4 to 5 degrees warmer than what it is right now. And to put that into perspective, when the world was 4 to 5 degrees colder, we were, or the planet was in the Ice Age. So in fact, the planet has already warmed by more than 1.2 degrees compared with pre-industrial levels, resulting in profound, immediate, and rapidly worsening health effects. And these health impacts are being seen everywhere on every continent with, for instance, cardiovascular and respiratory side effects of record heat waves and wildfires in Australia, North America, and Western Europe in recent years, undernutrition and mental health effects of floods or droughts in China, Bangladesh, Ethiopia, South Africa, the list goes on really, and the ongoing spread of infectious disease around the world. So the director of the World Health Organization quoted the Lancet Commission report from a decade ago now, saying that climate change is the greatest global health threat of the century. And 10 years on, we are seeing that the threat is very much still there and it remains. So it's not just about rising surface temperatures. As you may know, if you look briefly at the NASA's climate dashboard, we can see that some of the other key indicators of the planet's health, including, for instance, carbon dioxide emissions and sea level rise, are increasing almost concurrently with temperature, whereas sea ice, which traps heat and contains global warming, is on the decline. So some of these trends can be leveled off with net zero targets, although sea level rise, for instance, is set to increase even if net zero is achieved. And this has been confirmed by the latest IPCC report released in August just this year. Now, in addition to the overall change with time, there is an increased variability, so that there are more extreme events in the day-to-day weather, such as heat waves, floods, droughts, wildfires, and cyclones that we read about in the news every so often. And crucially, they all have a human cost. Then perhaps one of the most indirect, but maybe more stark consequences of human-induced changes to the planet is biodiversity loss. So the WWF recently investigated a sample of around 10,000 species, global species of the biodiversity, and found that in the last 40 years alone, approximately half of the species on the planet have been wiped out. So the era that we're living in has been called the age of great acceleration in terms of technological and socioeconomic progress. And ironically, that's led at the same time to the tipping point for anthropogenic climate change. And out of these maybe more exponential curves and wedges, perhaps the most important, a relevant one is this one at the bottom right, which shows that global warming can be controlled within the next 20 years with net zero, and that B, the time to do it is now. So now, with that, thinking of the links with health. So the role of environment on health is well known. The World Health Organization has been monitoring this for some time now, starting since the early 80s. And in fact, it is thought that environmental factors, including climate change and built environment related factors, are linked with a majority of the diseases in the world today, including both infectious and chronic diseases, as well as being a leading cause of mortality, which is responsible for approximately a quarter of the worldwide deaths that we see every year. At this point, it's also useful to emphasize that the chain of cause and effect is often extremely complex, and that actual health outcomes of environment and climate change, they depend on a combination of many factors, including socioeconomic ones, which influence public health infrastructure, access to adequate nutrition, safe water, and effective sanitation, and so on. This is a diagram from colleagues at the London School of Hygiene, who led the Lancet Commission on Planetary Health. And I included it because it shows the impacts in three categories, really. So impacts can be direct, such as heat stroke from a heat wave, or respiratory illness from air pollution, or indirect effects such as malnutrition from food shortages caused by droughts or climate impacts on crop yield, waterborne infections from unsafe drinking water caused, for example, by flooding, dietary diversity loss due to biodiversity loss, and then long-term or downstream effects, for example, from climate-induced or exacerbated migration and conflict. So let's look at some of them a little bit more closely. So thinking about heat and the effect of heat on health, the biology of heat effects on human body is rather complex, and frankly, I would not be the right person to talk about it. But what we do know is that exposure to extreme heat can make you unwell immediately, as well as in the long term, and that even medications and drugs can increase our body's sensitization to and its response to heat. And indeed, in the number of heat-related hospitalizations and deaths around the world has increased by almost 50% in recent years, particularly and unsurprisingly in the elderly and those in under-resourced areas. The association between air pollution and mortality is also well known. So one only needs to look at the WHO's dashboard on this to get an idea. Air pollution has even been linked with higher COVID-19 mortality. In one of the first studies done on this in the US earlier in the pandemic, a higher incidence of COVID-19 deaths was seen in some of the more polluted areas in the US, with similar findings in the UK, where additionally a further link was found with ethnicity. So in the sense that ethnicity is strongly correlated with pollution exposure, with ethnic minorities in the UK more likely to be living in more polluted areas. And then the effects can be seen in other clinical areas as well, with, for example, the effects of environmental and climate factors on mental health, chronic pain, pain in general, and even in bone and joint health, just to name a few. So for a while, this issue of planetary health was thought to predominantly affect those of us least responsible and most vulnerable. And while that is still very much the case, we know now that all in all, it is a global problem affecting every continent, and from now on, every generation. And so what's that got to do with machine learning? And that brings us to the role of data science in planetary health. First, I think a brief mention of the field of climate data science. This is an area of tremendous activity for all aspects of climate research, including, for example, Earth systems modeling, modeling of future climate scenarios, weather forecasting, extreme weather prediction, and climate data curation and data quality, which is quite an exciting area in itself. And these are just a few examples. But our focus in this talk today is on planetary health, which can largely be thought of in terms of three areas. So data generation is the first. So what are the positives of technological advancements in recent decades is that today there is no shortage of data or variety of sources of data. So everything from person level to atmospheric level to Earth observation level data, there is plentiful of data. So an active area in data science is bringing some of these disparate and asynchronous sources of data together, extracting and curating useful data from it. And then the second, following from that, is the extraction of useful information or knowledge from these data. So this is where, for instance, rapid, reproducible, and globally representative data-driven analytics powered by AI and machine learning is playing a part in enabling impactful research to inform policy and enact change in real time. The third and perhaps the most critical and pressing direction is that of climate adaptation. So by which we mean adapting entire health systems to a rapidly changing climate. In terms of adaptation mechanisms, one key area is that of early warning systems. So traditionally, early warning systems, for instance, for floods or disease outbreaks, they were generally based on local knowledge and experience and word of mouth mechanisms. Through AI, big data, and high performance compute, which are, as we know, the three key components of advanced analytics, now intelligent early warning systems have been developed, which have the potential to provide advanced warning of extreme weather and climate events. So such systems for early warning of heat, for instance, are already in place in places like Shanghai, several cities in Europe, and there's even a system in the US, in Philadelphia, to name a few. And the same is true for flood prediction systems, where, for instance, machine learning models using image analysis technology are supporting local knowledge to provide monsoon warnings in India and Bangladesh, where monsoon is a big annual problem. Then prediction of disease outbreaks is another area where informatics is involved increasingly. So these images are from some work done by scientists in NASA in 2017, modeling Earth observation data from the Landsat series of satellites to predict malaria outbreaks in the Amazonian region of Peru by modeling human and environmental activity, both with and without a malaria outbreak. Similarly, in Singapore, a weather-based system has been developed to forecast dengue, which is another mosquito-borne disease, which can predict a new peak 12 to 13 months in advance. So almost a year in advance of the outbreak, which means that national response systems have enough time to respond, which is what can be critical in these disaster management situations. Then another area where data science is involved in combating environmental and climate issues is tracking and monitoring of air pollution. So advances in sensor technology and advanced analytics have allowed air quality data to be leveraged on large scale. Two examples are the London Air Quality Network and the New York Air Quality Network, where sensors can be used to monitor and predict levels of air pollution. And through machine learning models, tools have been developed that can communicate via wearable devices and act as personalized early warning systems for those suffering from chronic COPD or what others vulnerable to more high levels of pollution, like asthma patients. Remote monitoring of patients or e-health has also shown potential for self-management and remote management of chronic conditions such as COPDs, which I referred to earlier on, kidney disease, diabetes, monitoring of women in pregnancy situations where they cannot have access to healthcare. They don't have direct access to healthcare. So this is an example from our own lab at the University of Oxford, where data fusion and machine learning models were trained on hundreds of thousands of hours of patient vital sign data, such as heart rate, breathing rate, oxygen saturation, blood pressure, and temperature, to develop what's known as a patient status index, such that if the index crosses a certain threshold, the patient care team can be alerted remotely and come to the patient's aid. This technology has also been deployed more recently for remote monitoring of COVID-19 patients, for the monitoring of their oxygen levels during the ongoing pandemic by colleagues at Oxford. Then, speaking of the COVID-19 pandemic, the response to COVID-19 healthcare, the whole pandemic, in a way summarizes many of the ways which informatics can be involved in adaptation of entire health systems to a pandemic, but more generally speaking to climate-induced changes. So from diagnostics to clinical risk assessment tools to developing vaccine prioritization strategies via risk prediction models, to developing deep learning for modeling disease phenotypes, and in general to contributing knowledge on this new disease, relatively new before 2020, which is too much to fit on this slide. And of course, researchers are working on COVID all around the world. The examples here on this slide are just limited to some of the work done here in Oxford, including some of our own labs work, but really a truly global effort, including a lot of work from the AI and data science community. So beyond these direct applications that data science is driving, as we know, some of the modeling to plan for the future, such as modeling for cooler cities resilient to higher temperatures, smarter transportation with less carbon footprint, and generally a future based on renewable energy. As with everything, AI or informatics also has a carbon cost. So some estimates, for instance, suggest that a single training and tuning of an NLP model can have almost half the CO2 emissions of a car in its entire lifetime, which is quite an amount. And the bigger computes can have even bigger footprints. So there is a move towards both ethical and responsible AI, and move towards more move away from red to more what's known as green AI. So artificial intelligence, informatics, data science, these are already pervasive in health technologies and beyond really, and are in everyday use. Although some of them are not without their share of controversy. What are some of the challenges going forwards for the data science community and planetary health? And what can be areas of interest to data scientists? So that brings us to the third and last part of this talk, um, which is a vast topic on its own, and can be talked about in its own. But I will focus here on the issue of planetary personalized health. So if we look at the framework for personalized planetary health analytics, at the heart of it is, of course, data, and to be specific, patient level data, by which we mean that, for instance, for a given patient, this could mean information on their socio-demographic background, such as age and sex, occupation, then any medical conditions that they've been diagnosed with by a doctor, any medical lab tests like blood samples or X-rays or MRIs, and any medicines that they have been prescribed. So this is what we might call raw patient level data, which would then need to be pre-processed and cleaned to be used for research purposes. And the next step could be what might be called phenotyping and discovery stages. So this is where we might do some feature engineering to, for instance, select some of the useful features belonging to a patient and then to fit models to that data. The models will in turn depend on the nature of the question that is being studied. Typical cases in healthcare informatics can be about learning certain health outcomes, for example, the risk of cancers or heart disease, or about understanding what that means in terms of the burden of these diseases to healthcare resources. So the area of health economics. Now, in a way, planetary health analytics was an extension of this framework of patient level analytics, where the broad idea is to add in environmental and climate related data to the raw patient level data and get to the same questions of health outcomes and resource utilization, but by using knowledge from the person and the person's environment. And there are several challenges along the way to do this. So to begin with, these data from the environment can be fundamentally different to patient level data. So they can come from different sources and they can be recorded in different ways. For instance, if we look at just temperature, this may be derived from weather-based stations, from gridded data, from satellite imagery, or even citizen self-reported data. Then these data may not be synchronized in time with each other, as well as with the medical data for the patient, which will be typically measured along very different timestamps. So the consolidation of these different data using advanced curation approaches is one active area of planetary health analytics, where data scientists are involved. Then next, in order to add some of these environmental variables into a patient's record, they need to be linked to the patient level record in some way. A linkage of these geospatial data with health data inevitably depends on attributing for instance, latitude and longitude data to the person level area or zip code. And this is a challenge because person level data is de-identified usually, which means that location information may not be available to prevent it being used to re-identify patients, which is a privacy concern. So further, it could be constrained by the granularity of the patient location information, even if it is available, which could be zip code or area level or census tract level. So this reconciliation of data and linkages is an area with a lot of opportunity for building big geospatially linked health and environmental data with the potential to answer a whole sort of breadth of planetary health questions and have impact in terms of policy. Okay, so say that we have linked data. We've overcome the previous hurdle and we have patient data linked with environmental data. We could then arguably move to the fun part, which is the data wrangling or the phenotyping and discovery stage. And this is our territory, right? Because as data scientists, bring us the data and leave the rest to the data scientist. But now there's the data quality hurdle to cross, and really any data science talk cannot really be complete, I'm sure you'll agree, without a mention of data quality. So, and again, that is in itself a talk in its own right. But just to give one example, let's look at the instance of heat, for example, information on heat and how it's recorded. So the International Classification of Disease, the ICD-10 classification, it contains specific codes for attributing death from exposure to excessive natural heat and excessive natural cold. Sorry. However, medical records will not typically include information on the weather conditions at the time of the event happening. So if someone has been exposed to extreme heat or extreme cold, and if they've unfortunately died due to that, the related surrounding information will not be contained in their medical records. So the recording and capture of heat-related events in the database is generally incomplete, or does not have enough information to be used sufficiently in research. Further, there's no standard or universal definition of heat or even a heat wave. And this can be important since, as shown by the two studies on the screen, even small differences in the definition of heat can change findings significantly. In addition, there can be general issues that affect all observational data, such as missingness of information, issues of accuracy of coding, such as duplicacy, discrepancy of records, so there being multiple records for the same person on an individual, and so on. And why is this important? Because as we know, any model is only as good as the data behind it. So getting data quality right is quintessential for developing models that are both reproducible, but also reliable and can be used in actual clinical practice in this case. So now if we go back to the first part of the talk, we might remember that planetary health is an issue that is affecting everyone on the planet. So what we want to really aim for is models that are globally representative, solutions that are globally representative and inclusive, and we need data that are similarly globally representative. But what if the data that are available to us are only representative from certain parts of the world, because that's where they have been collected or recorded? Or more typically, let's say there is some data being generated in various places around the world, but these data, they all look different and they all follow different standards, such as this analogy, which I've tried to put on this slide here with the electrical standards. So you have data that is coded differently in Japan, to USA, to India, to China, to Europe, and so on. And you may be surprised, but this is an extremely common scenario. And so one major opportunity area is that of standardization. So building what is known as a common data model, in which individual databases can be mapped to a single common data model, and they all understand and follow the same vocabulary and language, and they can be used by everyone in any country. And that can be really powerful for producing reproducible global evidence-based research. So the observational health data scientists and informatics collaborative as an example of such an effort, where data scientists from across the world are working with health experts and environmental data scientists to build a common data model. If I remember, there are around more than 25 countries involved in this effort from 6 continents. And as a data custodian or data owner, your input is that you need to worry about mapping your database to the common data model. And then there's no further data sharing or data transfer involved, but standardized research can be implemented in each of these databases in parallel and simultaneously. And so this approach is fast gaining recognition as one of the more best practice approaches in rapid, reproducible, and open science. And this is something I can discuss more if someone is interested in the chat later. But coming back to the framework for planetary health analytics, the key considerations are as listed, and these are all active areas of research within data science. So talking of best practices, one thing to maybe stress at this point is that it's also important not to work in silos. So contextual knowledge of the environment and knowledge of epidemiology can be quintessential to answering planetary health questions. Particularly, we're not so much about the interplay of multiple environmental and health stressors is clear to anyone, and particularly to those of us who are predominantly data science related. So this is just something about the Public Health England, who have embraced this vision of planetary health analytics, and they're developing a platform for data science and epidemiologists to collaborate through an easily accessible interface and download customized data sets for research purposes. And this is open to researchers globally, should you be interested to have a look at the Public Health England website. And then there are several initiatives around the world to leverage big data and artificial intelligence for planetary health solutions, both at regional and global levels as well. Finally, while the clock is ticking, there are some positive signs for planetary health, and as well as the potential for co-benefits from an overall health systems response to our changing climate. There's even a suggestion, believe it or not, that AI can help to meet almost half of the net zero targets set in the original Paris 2015 agreement. So AI can have a big role to play. And then you may be aware of communities such as the Climate Change AI Initiative and Future Earth, which embody the vision of a concerted AI solution to every climate-related problem. There's even a call for data scientists to sign up to their respective areas of interest and contribute to this sort of fight against climate change. Then moving towards the end of the talk, I guess a reminder that I always try and keep in place is that AI is not just about replacing human knowledge, but more about augmenting it and supporting it. And this is based on an advice by more than 100 AI experts, including the late Stephen Hawking, advising of the same. So on that note, I guess I'd like to move to the finish by really going back to where we began, and to say that while yes, there is a real and present threat in the form of a changing climate and its impact on human health, there's also a great opportunity. So we know there's no shortage of data, no shortage of analytical power today. So as a community and as an individual data scientists, it's really up to us to decide how to use that to our advantage and to do our bit, and really to have impact that can bring about the changes that are needed. Planetary health is an area where one of the areas in which I hope you've been persuaded that all of us can play our roles, central role really, with tools such as data science at our disposal. So with that, I'd like to end the talk, and I'd like to thank the many colleagues whose research was used in this talk, and acknowledge the support from our funders, and most importantly, thank you to the audience and the organizers for your time today.